You're wrapping up an afternoon at the beach with a breathtaking sunset. It's starting to get a little dark, so you take out your phone to memorialize yourself set against the fiery glowing sky. Later, you look back at your photo and realize that in the dim foreground you appear grainy and dull. How is this still the case after so many years of mobile camera technology development? Your color camera is surprisingly inefficient and loses almost 70% of the light coming into it. When you take a picture, the scene is projected by a lens onto an array of sensors. These sensors are grouped into sets of 4, each one responsible for recording how much of a specific color is present at this point in the image. Those colors are categorized by bands of wavelengths. Red contains the longest wavelengths and blue the shortest. Think of red like a basketball, green like a tennis ball, and blue a ping pong ball. Each sensor has a filter on top of it, which only lets through certain wavelengths by checking what size they are. All the balls that are the wrong size are thrown away, meaning this filter discards 2/3 of the light that hits it. When there isn't a lot of light around, at dusk for example, lowering the signal in this way makes for noisy and grainy pictures. What if instead of rejecting the wrong wavelengths, we redirected them to the correct neighboring sensor in the group? Then, each location would still monitor a specific color, but no light would be wasted in the process. When a beam of light hits a material like glass, it can change direction. A curved lens, for example, bends light to focus it, but mostly acts the same on different wavelengths. It turns out if we carve tiny patterns in that glass at resolutions finer than the smallest wavelength, the varying size balls of light that hit it bounce around and shoot out in different directions. By simulating how light interacts with these complex shapes, we can search for and ultimately design patterns that send each wavelength to a precise location. Some can pass directly through, while others are routed to the appropriate neighbor. Once we know what pattern to etch into the glass, the problem becomes how to make something so complicated and small. The device I described is the size of a camera pixel, with patterns 10 times finer than its width. Fortunately, techniques to fabricate devices like this drive one of the largest industries. The computer chip in your laptop is made of a dense electronic circuit, wired together through a three-dimensional network of metal connections with widths small enough to generate these intricate patterns. By replacing those metal connections with glass, we can make cameras that are 3 times more efficient. This means higher quality pictures, better low light and high speed imaging, and sustained performance at ever-increasing camera resolution. Thank you.
Thank you.